recap to where we were at. So we talked about our independent, started talking about independent sample t-tests. This forms the basis for like 80% of the stuff that you're going to be doing in terms of analyses and things along those lines. We got, at least in group-based stuff, right? We've got group A, group B. We've got population A with some unknown mean value, population B with some unknown mean value. We can't directly assess the population, and so what we're going to do is we're going to draw samples. We're going to draw samples from both of these, and what we want to do is we want to get a sense for whether or not we have enough evidence to conclude that the mean of population A is probably different than the mean of population B. Right? So same setup. Our null hypothesis is that mean 1 minus mean 2 equals 0. Difference between the population means is 0. Scores were likely to be drawn from populations having different means. You don't have to say all of these things, but just sort of multiple points of ways of interpreting this versus our alternative hypothesis here. Again, our goal to try and see, is the difference between the mean values of these two groups large enough that we can reasonably conclude that they were drawn from populations having some different value for their mean. Talked about our assumptions, and we're going to jump into this. We're assuming our outcomes are continuous. We're assuming independent observations. We're assuming that the distribution of sample means from which each one of these samples were drawn, or the distribution of sample means for each population from which these samples are drawn is going to be normal. And then this homogeneity of variance, right? We're assuming that the variance in both of these samples, or in both of these populations, is equal. So they got a different mean. We're assuming the spread of scores is relatively similar. Informal assumptions don't contain outliers, equal sample sizes. If we got 1 or 2 people different, not a big deal. If we've got a lot of people different, that starts to make our test less robust to violations and things along those lines. So we talked about standard error of the difference in sample means. Discussed that when we're calculating the standard error here, because we're working with variability in 2 different samples, what does that do to our standard error essentially, Rajiv?
What was the question, please? What is the
So
question?
if I'm working with the standard, if I got calculating my standard error for 1 sample, but then I go and now in my 2 sample test, now I'm looking at my standard error in 2 different samples. What does that do to my standard error? Does it increase it or decrease it?
It increased.
Increases it. Basically, it doubles your standard error essentially. If you compare the formula for standard error for our single sample t-test with our independent sample t-test, basically you've got this term and then you've got this term again. It functionally doubles your standard error. And the reason for this is we're working with variability in both populations. If we're comparing our sample against some reference population or some reference value, the reference value is the reference value, right? There's not variability around the reference value. The reference value is what it is, right? But here, we're testing the difference between 2 means. We're expecting variability in both means, and so what we end up having to do is calculate and account for both of these variables in both distributions. And so what ends up happening is the standard error, the difference between our 2 means, ends up being systematically larger than the standard error if we're just using 1 sample t-test, okay? And so this is just, we went through talking about kind of conceptually what's going on and why we need to account for that. But we talked about what happens if our sample sizes are different sizes. Stephanie, when do we tend to have, do we attribute more precision to our sample that with the larger number of people or our sample with a smaller number of people? Larger, right? And so it's probably not a good idea to just treat these, if we've got different samples with different sizes, it's probably not good to just treat them as if they're the same, because we've got 1 sample. We would expect that all things being held equal to have a more precise estimate of our parameters than the other sample, right? And so what we do, we assume that in our homogeneity of variance, we assume that our variance is going to be equal, but we know it's never going to be the same, right? And so what we do is we then create a pooled variance estimate that gives us the the weighted average of our sample variance, right? You'll get very familiar with this equation. You'll use it a lot, okay? But basically, we're just taking the number of people in the first sample minus 1 times that sample's variance plus the number of people in sample 2 minus 1 times that sample's variance over n plus 1, or n1 plus n2 minus 2, okay? So what ends up happening in this situation is the sample that has more people in it, we're assuming that the variances are equal, but because our actual point estimates are going to be different to some degree, what we're doing is we're giving more weight to the sample that has more people in it, okay? And so our formula for our independent sample t-test is going to be mean 1 minus mean 2 over the square root of our pooled variance over the number of people in sample 1 plus the pooled variance again over the number of people we have in sample 2. That's going to be our standard error of the difference in means. Okay, be careful. This is variance, not standard deviation. Okay, this is sample size, not degrees of freedom. Make sure you're clear on those things. Okay, and then degrees of freedom for our full test is the number of people in sample 1 plus number of people in sample 2 minus 2. Okay, then we talked about effect size. So as soon as we get into our independent sample test, we've got a lot of different options in terms of our effect size. One, the raw difference. Raw difference is nice if we have some metric that has meaning, right? If I'm talking about time or dollars or miles or years of life, these are things that have intrinsic meaning, and I can just say, this is our best estimate of the difference between group A and group B, and that's kind of interesting. But with a lot of the stuff that we do, our arbitrary scales with their arbitrary scores don't have a lot of intrinsic meaning, and so it's nice to get a standardized effect. We talked about Cohen's D. This is easy. It's the mean 1 minus mean 2 over just the standard deviation. Morgan, what's our concern with Cohen's D? What's the ambiguity we're not comfortable with here?
If the sample sizes are different?
Not the sample sizes. I mean, because sample size doesn't go into our effect size, right? That's what the nice thing about effect size. Effect size doesn't have anything to do with our sample size. What's the ambiguity with Cohen's D in an independent sample test? Someone give her a hand? Yeah, which standard deviation? Because Cohen just says S, right? And why can Cohen just say S? Yeah, we're assuming they're equal, so Cohen doesn't care. He's like one or the other one. Well, Morgan, or Alex, what's the practical difficulty, the ethical difficulty, if I just get to choose which S I want to use?
Because you can choose the S that lends itself to your hypothesis.
Or more specifically the smaller one, right? Because the smaller standard deviation is give me the bigger effect size, which I'm probably going to like better, right? And so from a theoretical standpoint, Cohen doesn't care. He's like, I don't know, S, there should be the same, right? But from a practical standpoint, if I'm going to crank this out by hand, I got to choose one value or the other. I'm probably going to be tempted at least to choose the smaller one, right? And so we've got different variations on Cohen's original formula. Glasses delta, who have I not picked on in a minute? Sam, tell me what is going on with glasses delta. Why would we, what would be the situation in which glasses delta might be an attractive metric for our effect size?
When we have a control.
Exactly. Choosing our effect size is all about our standardizer. What's the metric it's all gonna be standard deviation units. Standard deviation units of what, right? If we have a nice control condition, something that exists out there in the real world, glasses delta is nice because we can just say, we find that group B exceeds group A by 2 standard deviations, and that's based on 2 standard deviations in the normal population, right? Because that's a reference group, that's everybody, like that's cool, I know what's going on there, right? And so if I say that I have an exercise program and I say that people on my exercise program you know, a 0.8 standard deviation decrease in overall body mass relative compared to the general population, right? That's something nice, right? So you're comparing people in my exercise program versus people who aren't doing anything, looking at the variability in body mass around people who don't do anything and seeing where I'm at. That's kind of a nice thing to, in terms of interpretive properties. But sometimes we don't have a good comparison group, right? Sometimes I bring people in and I've got group Angeline that I did this to and group Lauren that I did this to. I've done something to both of them, right? So there's no real good comparison group. What do we got going on, Lauren, with Hedges G? What have we done there?
Well, you don't need, one fun fact is you don't need to pick which standard.
Yeah, why not?
Because you're using the variance. Pooled standard deviation.
Pooled standard
Yeah.
deviation. Also, don't use a variance as your standardizer for your effect size because it's
Sorry.
considerably smaller than what you want them to be,
Word
right?
vomit.
Yeah, exactly right, right? We're just gonna go through, and this is nice, because we're just gonna use the same variance estimate that we used in the calculation of our standard error for our effect size. And this is gonna be advantageous when we start calculating, wait for it, confidence intervals around effect sizes, right? You'll wanna make sure that you're using this correct standardizer. And so this is nice, probably in most cases, this is the most common standardizer that you'll see, but it's always important to tell people what you use as your standardizer for your effect size, and then, at least for the purposes of this class, telling me why you thought that was the best one to use, okay? And then we talked about Hedges unbiased G. It's just, we know that in small samples tend to inflate our effect sizes. And so what we have is we go through with Hedges unbiased, we calculate our Hedges G, and then we just multiply that by a correction factor. As our sample size increases, our correction factor shrinks, right? But for small samples, we get a pretty big downward correction to try and watch out for correction for small sample bias. We also talked about this up here from secondary analysis. Do I want you using these in your homework assignments? No, why not, Alex?
Just you answer this. Because they're a mess.
No, they're not necessarily a mess, but you have access to data, like, just
Oh,
use
yeah.
the data, like, it's your data, like, you're looking at it, like, don't just calculate them right? And these tend to be approximations based on, but if I'm interested in calculating effect sizes from a manuscript that's been posted out there and they haven't given me their means and standard deviations, like strong researchers should, but if they've given me other information, I can go through and start to approximate the magnitude of their effects based on their T statistics, okay? But in almost all cases, you'll have, not in all cases, but almost all cases, if you have access to the descriptive, if you've got stuff that you can use to calculate this, just calculate them this way, okay? Walk through an example, then talk about what happens though when our variance estimates aren't equal, right? What if we have strong evidence that the variance in our population 1 is quite different than the variance in population 2? What we do is we end up having some corrections for this, right? What we'll end up using in SPSS is our Levine's test, and what this is a correction for your test statistic and your degrees of freedom to help start to adjust for problems in your violations of your test. This becomes important, and so a couple of people did an excellent job talking about how our assumptions about our distribution of our test statistics, right, is fantastic. We can pull out very, very precise probability values under certain circumstances. If we haven't violated the assumptions of our tests, our probability estimates are quite good. As soon as we start violating those assumptions, all that goes to hell, right? And what ends up happening is we start to have less and less faith that our probability estimates are correct as soon as we start violating assumptions, because the T statistics that we're calculating under the violation of assumptions don't have the same distribution as the t-statistics that we would expect if we hadn't violated assumptions. And this is the crucial thing. This is why it's always important to go through and take a look and say, am I reasonably consistent with my assumptions? Good news is for our t-tests, for our means-based tests, these are typically robust to most types of things, okay? If we have a violation of homogeneity of variance, we're still pretty good, still not too bad, assuming that we have equal sample sizes, right? If I've got sample size 1, sample size 2 about the same, but I violated homogeneity of variance, probably not going to impact my test too much. If my scores are hugely non-normal, right? Again, our assumption is the distribution corresponds to the distribution of sample means, not the actual observed values. But sometimes you can't just look at it like a crazy distribution of your observed scores and assume everything's okay. But they will be as long as you have a reasonable size n and you've got distributions that are shaped in the right same direction. So I've got group A and group B have positive skew. I've got reasonable size samples in each, I'm probably going to be okay. But if I've got group A is skewed positive, group B is skewed negative, now all of a sudden I've probably got some issues, right? Issues when we're not robust is when we start doubling down on violations. If my distributions have a very different shape and unequal variance, then I start to have problems. I have less evidence or less confidence that my test is robust to these effects. If I have unequal variance and unequal sample size, this is nice because we can kind of guess which way this is going to bias our tests, right? So if I've got 10 people in group A and 50 people in group B, and these two things have unequal variance, the larger sample has larger variance, my test is going to be too conservative. I'm going to reject the null hypotheses, or I'm going to fail to reject more often than I should. If the larger sample has smaller variance, weighting things towards the smaller end, I'm going to have too liberal a test. I'm going to reject the null hypothesis more often than I should, right? If I've got violations of normality and small sample size, that's also a problem. Again, if I'm getting samples 25, 30, I start to be better about things, but this isn't like a clear, bright line, a magical number, right? You should still be wary of some of these things. Okay, so what we're going to do is we're going to jump in and work with some data. If you want to grab your independent sample t-test screening sheet, and pull up that MVA test data set again. Okay.
The same data set we've been working with.
Yep, same one we've been working with. Okay, so what we've got in this situation is we've got, what do we want to do here? We want to take a look at differences in, again, when we're still working with people who've been exposed to serious car accidents and people who are coming in with post-traumatic stress disorder. But what we're going to do is we're going to run a test, and the question of interest is whether or not men and women differ on certain types of characteristics. So if we're talking about male car accident survivors and female car accident survivors, both who have PTSD, what we're interested in is, for whatever reason, is whether or not we see differences in marital satisfaction across these two groups, and also whether or not we see differences in reporting style, right? Our PRI is our Marlowe Crown, social desirability. Do we see among individuals with PTSD, do men and women differ in terms of their willingness to sort of endorse things that are common but not always exciting to say about ourselves? Like, sometimes I lie, sometimes I do things on purpose that I know are going to hurt people. Sometimes I talk about behind people's back, like these types of things, right? I don't know why we're looking at these things, but we just are, because this is our research question and it ends up being nice for demonstrative purposes, okay? So what we're gonna do, we've got 2 samples here. So what do we need to do first before we run through and start? Can we just run on one screening if we're running 2 samples? Nope, we gotta look at distributions of both, right? And so our measures of interest are this Locke-Wallace and this social, the Marlowe Crown here. And so what I'm doing, let's see, we don't have a large set, but if we did have a large set, I'm just going through and sorting both of these by ascending. And what does that do when I sort both of these by ascending? Puts my person who, case 132, who doesn't have scores, puts them at the top, right? And so what I'm gonna do is I'm gonna say, all right, I'm gonna go save as, call this scrap, all right? And I'm gonna clear that person out, okay? They're not gonna be in my sample anyway, I'm just gonna get rid of them so they're not fooling things around. As you're going through and working on the data here, wanting to make sure that you're not changing any scores necessarily, unless you've got a case that has a value that's not a real value, or you've got a case that is missing data, you can just go ahead and get rid of those. Okay. So, gone through and we've got our marital satisfaction, we've got our Marlowe Crown social desirability, and then we've got our gender variable here. And so these are all married couples, or not married couples, married individuals who have been involved in car accidents. And what we want to do is we want to see whether or not men and women are different in terms of their presentation style and their marital satisfaction. So what we're going to do first is I'm going to go to Data, Split File. Hit that, and it's going to say I want to organize groups by output. And the groups that I want to organize is going to be gender. Okay. And what this is going to do is it's going to split my data set up, and it's going to, any analyses that I run, it's going to run one group for men, and it's going to run another, another set of analyses for women, right? This is helpful because when we're screening our data, we want to take a look at distributional assumptions in men, distributional assumptions in women, and what we can do instead of splitting these up into different data sets or something like that, we can just tell SPSS, hey, run these 2 groups differently, okay? So we're going to go through and we're going to paste. Got our data set there, okay? And now what we're going to do is we're going to go analyze descriptive statistics, descriptives, okay? And we want to look at our Locke-Wallace marital satisfaction, our Marlowe Crown. On options, we get skew and kurtosis values. And then what I'm going to do is I'm going to say save standardized values as variables. Someone remember what this is going to do for me?
Print them in the Z-statistics.
What's that?
Print them in the Z-scores.
Yeah, it's going to give us Z-scores. Morgan, why do we want Z-scores?
They're standardized.
Hmm?
They're standardized?
Yeah, what am I going to use those for? Eventually. Comparing, yeah, what specifically am I going to use these Z-scores to look at some point down the road? People remember? Sam?
Outlier?
Outliers, yeah. Wanted to see if we've got variables out there. It gives us a standardized score, right? So, got all that put together, gonna hit paste. And then what I can do is I can just go through and highlight the whole thing and run this. Okay. So, someone give me a sense for what's going on with these initial data. Rajiv, tell me, if we're looking at the men, tell me what we're seeing here in terms of our scores.
So the minimum, the mean for the log wall is total falls under the range of 45 to 140.65.
Okay.
If we see the skewness, it's less than 2, so I think it's good, I guess, in the skewness. I guess it's
Yep,
less
yep,
than 2.
skew, not too.
Yeah.
Worried about skew, what about kurtosis?
It's good, I guess, because it's less than 8, right?
Yeah, I mean, the benchmarks on skew and kurtosis are a little bit, you know, in general, like, less than, both skew and kurtosis are less than 2. This one's has negative kurtosis. What does that distribution look like? We are leptokurtic.
Yeah.
No one remember the picture,
Yeah.
right? This is burned in your brain, right? It's very, very thin with thick tails, right? And so some negative kurtosis that we have here, or no. Negative kurtosis is platykurtic. It's boxy, okay? Like a platypus. Which we've got probably more negative kurtosis than, you know, would be, I mean, we'd like it to be less than 2, but I mean, if it's less than 8, what's the big thing that should catch your eyes in terms of what's going on with the men?
The standard deviation,
I don't know, the standard deviation in and of itself is concerning. What anybody? Yeah, what is it, Alex?
There's only 5.
You have 5 people. That should flag me, as this is potentially kind of an issue. I've got a sample of 5, which is really small, right? And with 5 people, that's a small sample where I'm not terribly confident that my distribution of sample means is going to hit normality anytime soon, right? It's just really small. You're going to have problems with power. And so what we want to do with this first piece, one, take a look at your number of people you have in your sample. Make sure that you have the same number of people in your sample that you think are in your sample. If you think you have 20 people and you've got 15, you need to go through and figure out where your people went. Wanting to look at the minimum and the maximum. Why do we look at the minimum and maximum? 70?
To see if they're like possible.
Exactly, right? If my scale runs from 10 to 50 and I've got a sample and I've got a score of 8 at the low end, something's gone wrong because you can't have a score of 8, right? Or if someone has a score of 60, that's wrong because you can't have a score of 60. Always want to take a look at your minimum, maximum, making sure everything's kind of falling within the range that we should. I'm going to put on these examples and in the assignments sort of the range of reasonable values, and unless there's some explanation for why someone might fall outside of that, I wanted to take a look at that. Take a look at mean standard deviations in our skew and kurtosis values. Want to make sure that those aren't. We're going to go through and look at things graphically, but want to go through and to see. So maybe some negative kurtosis, but with a sample of 5, am I super sure that things are going to approach a nice normal distribution? Probably not. The 5 scores are probably going to be all over the place. Okay? With the women, we see 21 people, right? So we've got already, we know that we've got different sample sizes, right? My number of women are 4 times as many people in my female sample than my male sample. So that's something I want to tuck away in the back of my head and say, that's something we want to think about. Values all fall within range of the plausible range of the scale, which makes me happy. Means, standard deviations, skew and kurtosis, things are looking better here. No real concerns. Some negative kurtosis here, but probably what might be contributing to lower skew and kurtosis values or at least lower kurtosis values in my among my women than my men. think so.
The sample size.
Yeah, you got more people, right? It's hard to build a reasonable distribution when you got 5 folks in it. It's hard to build a reasonable distribution when you got 20 people in it, but you're doing better than 5, right? So these are the types of things you want to go through, think about, not only, hey, are there red flags, also what might be driving some of these things we've got going on, okay? So questions about anything that we're looking at in our descriptive statistics? Yeah?
Could you remind me of the skewness and kurtosis statistics that we're looking at?
What about them?
Like, I can't remember how you interpret them
Yeah.
based on these.
So ignore the standard error. We don't care about that piece. Looking at absolute values, in general, skew kurtosis values less than 2 are okay, right? 0 is perfect normal, but we never get perfect normal data. We don't even assume perfect normal data. And so what we want to do is just make sure that we don't have values that are starting to get large. Here, I'd probably in my write-up note that we've got kind of negative, particularly 2.5 is, that's some level of negative kurtosis in my marital satisfaction scores for my men, but probably not something I'm not too spooked yet, right? Again, kurtosis, and we'll talk about this. Skew kurtosis, the impact starts to reduce as our sample size gets larger and larger. When we get into regression analysis, we'll talk about how, once we get to a certain sample size, our effects start to become fairly robust to skew and kurtosis and our univariate stuff, as long as it's not completely ridiculous. All right, so what we're going to do now, if you flip your page here, we're going to I'm going to do something different here. I'm going to go through and I'm just going to right click and sort ascending. As soon as I sort my data, that's going to kick off my split file, okay? And so on your sheet, what you can do is this has just graphing out your histograms and your then your box and whisker plot stuff with your split file stuff on. But I'm going to show you a shortcut on how to do this. It'll make it easier. If we go to Analyze, and down to Descriptive Statistics, and hit Explore. All right, I want to look at distributions for Locke Wallace and Marlowe Crown. What I want is these distributions to be split up by gender. So I'm going to put gender into my factor list, and that's going to give me different sets of data for these 2 groups. And then I'm going to click subject number, and I'm going to say label cases by. What this is going to do is it's going to, when we run our box and whisker plots, if we have values that are standing out as extreme values, what this is going to do is it's just going to start labeling those values with the subject number as opposed to just their order in the case, okay? If we go to statistics, cancel that, plots. Turn off the stem and leaf. I don't care about the stem and leaf plot, but turn on your histograms here. Okay. People follow me? All right, then hit continue. All right, so we've got the things, our outcome variables we're looking at. We're splitting them up by gender, and then we're labeling cases by our subject number. I'm going to hit paste. And then what I can do is run all this. Okay. Should. There we go. Okay, so what this is going to do is going to be a little bit different than what you have on your sheet, but this is easier than going through your graph and just getting different ones. It's just a more efficient way to run through this stuff. You've got, in your case processing summary, the number of people you have, it can tell you any missing data that's going on. Then your descriptives. This is going to give you a whole bunch of stuff that is useful in general, but I just kind of like the layout of the regular old descriptives. But we get, for each group, for each variable, we get skew, kurtosis, means, variances, range, and stuff like that. If you are fine just pulling stuff out of there, there's a nice way to get them too. I prefer just getting them in descriptors. I like the visual of that better. But this gives you all of that so we've got our, for our Locke-Wallace, we've got our men, we've got our women, and associated statistics. Same thing for our Marlowe-Crown. We have men, we have women, same thing. What I'm interested in is using this to get a handle on my histograms. So this is the distribution of my Locke-Wallace scores for my men. See my mean, my standard deviation. Alex, what do we think about that distribution? That distribution sucks, right? But what we would want to do is, why does this distribution suck? Because it's got 5 people in it, right? So when you're screening, what I would want you to do is say, hey, distribution is a box distribution, clearly not normal, however, attributable to the fact that we only have 5 people in this set, right? Oops. Our same thing, our Locke-Wallace scores for our women. How would we, Reggie, how might we describe this distribution in terms of its shape?
It's not normally distributed. It's approaching towards a normal distribution.
Well, what's kind of the feature, at least in these data here? What do we call a distribution that looks this way? Not negatively skewed. Bimodal, right? And this is the thing, I want, in your screening, want you all to be taking a look and saying, all right, what's going on with these data? Here, it looks like we have a bimodal distribution where we've got kind of a tiny little normal sort of thing at the low end of marital satisfaction, and then a sort of another kind of skewed at the higher end of that at the end of the satisfaction scale. What is one hypothesis we should always have when we see a bimodal distribution? What's that, Candace?
Oh, that you have 2 populations.
That I actually got 2 populations, right? I don't know, right? Based on the data that we have, but we might have 2 sets of individuals, one set of individuals who may have strong marriages and not strong marriages, right? I'm not sure, right? But anytime we have a bimodal distribution, to the concern that we might have collapsed 2 different distinct groups into one different group, or one common group. But in terms of describing this in your screening, we'd want to say histogram for the Locke-Wallace among female participants appeared to be bimodal, with one major mode at 130, minor mode at about 80 or something like that, right? Now again, is our assumption of our t-test about this distribution here? No, right? It's about the distribution of sample means. We still are working with a small sample. We've only got 20 people in this sample, but I mean, our big concern is that we don't have any like crazy outliers or something like that that's going to be dragging stuff around. Yeah, Sam.
So if we have a bimodal distribution, then that means we might have like a dimension that we didn't account for,
Yeah.
basically.
Yeah. There's potentially a variable in there that we're not accounting for. that might be relevant, right? So these are the types of things we want to go through and talk about. So in your screenings, wanting people to go through and say, all right, that's clearly not normal. We've got kind of a box distribution, but that's likely attributable to the fact that we have only 5 people in that sample. Histogram of, in terms of describing that. Then we've got our box and whisker plot. What do we say about our box and whisker plot? Things are looking all right with box and whisker plot, right? Same box and whisker plot for men. It's about as good as a box. It's about as symmetrical as a box and whisker plot can look like, right? But no extreme values. Same thing for the women. No concerns with the lock loss there, right? And so when you're going through and making interpretations of these things, if everything looks good, right, you can say histogram suggests or data appear to be approximating normal distribution based on histogram. Box and whisker plot indicated sort of no concerns with stuff, and that's fine. That's an okay thing to do, right? If there's if we're doctors, we would call these plots unremarkable, right? There's just not a whole lot going on there that would cause us concern. That's fine. But if there is something there, I want you to go through and talk about that, right? So. So that's our lock loss. Here's our Marlowe crown. Again, with the men, it's 5 people. There's not a whole lot going on there. For the women, I mean, they're looking, reasonably normal, given a sample of 20. Again, here, might say looks like some potential negative skew for the box and whisker plot for women, right? But nothing too much going on here. Okay. So, based on our evaluation of skew and kurtosis and our evaluation of our plots, do we have any notable concerns in terms of our distributions to this point? What do you think, Angeline?
Besides the fact that we have 5 males.
Yeah, aside from the small sample, right? Nothing too bad, right? It doesn't look like we have distributions working in the complete opposite directions. I mean, what things are, the bimodal for the lock Wallace for the marital satisfaction in the among women was kind of notable, right? We might sort of make a note of that, but it's not anything that would tell us that, oh, we can't proceed with our analyses. Okay. What's the last thing we want to check out as we're going through and running our screening, at least with the stuff that we can do in here? Maureen, what did we ask for at the very front end? Outliers, right, z-scores, right? And so what we can do then is I'm going to go through and I'm going to take my descriptive statement here and I just paste that down. And for my lock Wallace and my Marlowe crown, SPSS is nice. The z-scores are just put a z in front of whatever your variable is, and that fixes that, right? And then we don't want this save command. This is telling us to save z-scores. We don't need to z-score our z-scores. So we get rid of that. And all of a sudden we have our statement to look at our descriptives. Okay. We could also do this if you were to go up, analyze, descriptive statistics, descriptives, get rid of those two, throw in your z-scores here, turn off your standardized things, click off skew and kurtosis, continue and paste, give you the, and so yeah, here we go through pull skew and kurtosis out of this statement as well. All right, but it gives us the same thing. So as you start to do this, you're going to do a lot of screenings over the course of this year. You're going to get good at this, but you can start going through and moving things around with this. So here, whoops, going to take a look at our descriptives for our Z-scores. And Morgan, I'll let you take this home. Any concerns? What are we looking for here in terms of our Z-score distribution?
I don't know what your constraints are, I don't mind.
What's that?
I said, I don't know what constraints you're looking for. I know which ones I'm looking for in the context which I keep it.
Okay. So what in general? So why did we run? Why did we take a look at our Z-scores?
To make sure there's no outliers.
Outliers. And what would indicate an outlier, an extreme value that would trigger us to maybe do a little more searching within this descriptors table?
Z's above or 3?
What's that?
Are you doing Z of 3?
Sort of depends, right? Essentially, we're looking for Z-scores that are very large or very small, right? Now, what you decide is your threshold for an extreme value kind of depends on a lot of different factors. How many people you have in your sample, right? What you're measuring. All these types of things need to go in and think, because we're not just going to say anything above a Z-score of 2 or anything above a Z-score of 3 is going to be our outliers, right? If we want to tie this onto standardized normal table, 258 is P equal 0.01, 3.29 is less than equal 0.001, right? But again, this is something you should be looking at your graphs, your data, understanding what phenomena you're trying to take a look at in terms of determining whether or not you've got extreme scores. But here, do we have anything that looks like an extreme score? No, right? Our lowest score, it looks like it's about, well, what am I doing wrong here? I've collapsed this. I need to go resplit my file, right? Because something that might be a low Z-score, well, when I created my Z-scores, I had the file split when I created my Z-scores, right? And so SPSS is calculating Z-scores for men based on the mean values for men, and Z-scores for women based on the mean value for women, right? So when I go through after I turn the split file off, that's just telling me all the Z-scores, but still what I want to do is I want to take a look as I'm describing what's going on in my screening, range of Z-scores for men, range of Z-scores for women. So what I'm going to do is I'm going to go through and I'm going to, my sort cases, my split file command, I'm going to run that again, and then I'm going to run my descriptors on my Z-scores again. All right, and so now what we have Z-scores for our men, Z-scores for our women. Remember that everything that you're doing within this screening procedure for your independent sample t-test should be breaking apart men and women. Okay, so here we see for men, our lowest on the low end, about a little over standard deviation below, a little over standard deviation above. No concerns there. For women, on the low end, we're getting close to 2 standard deviations below for both variables, but just a little above 1 on the top end, right? So make sure that as you're going through running your screening for your independent sample test, that you're talking about things for men and women separately. Okay? Yeah.
Does the split case or the split files thing automatically shut off after?
It stays on until you go through and resort cases or something like that. So remember that I turned it off and then ran my descriptives for my graphs and stuff like that using men and women as my split variable. If I do that with the split file on, it's going to freak out and tell me something's backwards, right? Because it can't split men and women when it's looking at men separately and women separately. So you'll get the hang of it. You'll make a lot of mistakes, but it won't screw up your data at all. It'll just give you an error message like, oh, whoops, I got split file on. Anytime you sort your data, it turns it off. But then if you have it in your syntax, you can just reactivate it. Okay. So, went through, did all of this stuff. what, at the end of the day, is our concern? Do we have any concerns with our basic assumptions of our independent sample t-test? What do you think, Rajiv? Because in your summary, I'm going to ask you to go through, once you do all this, I'm going to like play the role of statistical consultant and tell me, is there anything in here that you should know about, right? You're going to, because I told you not to screw around with the data. So you're going to run the test I told you to run. But this is like your warning box, right? You're like, well, I'm going to do this, but these are the things that we should be aware of, right? Anything about these data that, at least to this point, would cause us to maybe question the inferences that we draw from our tests.
Talking about the sample size of male population, I guess.
We're working with a tiny, tiny sample here, right? 5 and 20. 20 is not big. 20 is really small. 5 is almost unreasonably small, right? Well, it is unreasonably small, but these are the people that we have, right? So would want to go through, and again, when you're writing this up, go through and take a look at your assumptions, right? We say that we don't have concerns about that all the values seem to be, or we had a missing value for one case. All the values seem to be plausible within bounds of what would be expected given the measures. Sample sizes are unequal, which might cause us some concerns, but doesn't look like we have concerns regarding the distributional properties or the distributions of our sample. So we might say, what's the one thing that we haven't tested yet in terms of our assumptions? Homogeneity of variance, right? And so you're going to have to go through and run your, because you'll get your test of homogeneity of variance when you run your t-test. But up to this point, only thing that we're probably concerned about is going to be our sample size. Okay. And then, because we've got discrepant sample sizes, if we do find that we have a violation of our homogeneity of variance or clear violation of homogeneity of variance, should we be concerned about that? Yeah, why is that, Stephanie?
Because at that point we're compounding the violations.
Exactly.
And you can end up with either too conservative or too liberal.
Perfect, right? And this is the type of thing I want you to kind of bring in back. Yeah, we have unequal sample sizes, which isn't a big deal because it didn't look like we violated homogeneity variance, or it might be something to be concerned about and notable that because our sample of women had larger variance than our sample of men, and because our women have more people in that sample, this could lead to a more conservative test of our hypotheses, right? Or maybe women have lower variance than men, and so then it's going to be too liberal a test, right? And so thinking about these things, kind of bringing this all together and sort of getting a deep understanding of your data and the potential warts that are going on in that. Questions about any of this stuff? Okay, cool. Let's take a break. Okay. Folks, let's jump into your single independent sample t-test sheet. Because that's pretty easy. All right, so we've gone through, we've run our screening, and I'll post, we had an example of kind of the format for your screening. I'll post another kind of like template for how I'd like those things laid out. I used to like let you do it because I wanted you to do your own thing and sort of hold this together on your own, and then it was a mess. So we'll go through wanting you to go through, and I may try to go through and post up just another screening example, like as a screencast, just to kind of give you some ideas on what types of things I might want to be looking for with some of this stuff. But we've gone through, run our screening, have no concerns or maybe some tentative concerns about potential violations of our assumptions, but what we're going to do is go ahead and proceed with our test. And so what we're going to do, I'm going to split or sort this again to make sure that my split file isn't on. I'm going to go to Analyze, Compare Means, and go down to my independent sample t-test. Then what I'm going to do is I am going to say I want to run a t-test on my Lock-Wallace and my Marlowe crown. My grouping variable is going to be gender, and then I have to hit define groups. Okay, this is nice because you can, if you had like a categorical variable with 3 levels, right? You say you've got elementary, middle school, and high school. You can go through and just use that and just tell it which groups you want to compare. Here, we've only got 2 values, so we want to compare 1 against 2, and then continue, right? So making sure that whatever you put into here matches your values that you've got there, however you've got that coded, okay? And then if up here in options, you can change the confidence interval you want. 95% is the default, but you can change that to 99, 90, whatever you wanted to, but then we're gonna hit paste. And here's your t-test. This is nice and easy. As you're doing lots of different t-tests, you can just go through and change your variables that you want t-tests on, change your grouping variable, things like that. But for this purpose of this demonstration, we'll just go ahead and run this. All right. And so after all this work, not a whole lot to touch base on, but up here in the group statistics, and again, this is when you're running these analyses, I want you to again be able to identify all the different pieces and parts and know what those things are and know whether they're important or not. Here in your group statistics, always want to go through, you've got numbers, sample sizes, means, standard deviations, and then SPSS calculates the standard error to mean for you, right? So if I wanted to calculate a point estimate or a confidence interval around my point estimate of 80.23, I can do that easily, right? I would take this plus or minus whatever the critical value of my t-distribution for degrees of freedom 4, multiplied by my standard error, the mean, and then that's going to give me the confidence interval around my point estimate for the mean Lock-Wallace value for men, same thing for women, right? So want to go through, make sure that the numbers here that I think I should have actually match up. And then I'm going to drop down to my independent sample t-test, okay? If we're looking first at our Lock-Wallace marital satisfaction scale, okay? First thing we see, Levine's test for equality of variances. We see we get an F statistic, a significance level. Sam, for my Levine's test, for my Lock-Wallace outcome, does it look like I've violated my homogeneity variance? No, why not? It's not statistically significant, right? And so what does this suggest then, Stephanie, in terms of my assumptions?
That although we may have some concerns previously, because our variances are the same, it will probably be robust to that initial concern.
And be careful here because our variances are probably not the same, but we don't have evidence that they're big difference, right? I like to use words like similar instead of same, right? That way we keep ourselves out of trouble. And so what might be the only caveat to interpreting this statistical test is saying, yep, I clearly have no evidence of a reliable difference between my sample or between my variances. Yeah, I mean, I have a wildly underpowered test to begin with, just because, I mean, I'm not shocked. All this is saying that I don't have evidence of clear violation of homogeneity variance, but I also have a hugely underpowered test, and so wanting to take that into consideration. Also, same thing, if I had a 100 people in one sample and 200 people in the other, and I found that I had a significant test, I might want to take that sample size into consideration that, well, I've also got a pretty big sample, and I've got probably a pretty sensitive test here. What you can do, and would strongly encourage you to do, is go up through and take a look at your variance estimates here, right? Now these are standard deviations. The assumption isn't about your standard deviation, it's about your variance. But if we take a variance estimate of, say, 30.37, and then I square that with 922 and 24.41 and square that is 595. I mean, they're not exactly the same, right? But it's at least telling me that I don't, at least based on convention, I would go through and evaluate this, assuming that I haven't had a severe violation of homogeneity variance. Okay. And so, assuming that that's what I do, Angeline, which one of these rows should I be interpreting? Top one. Why is that?
Because equal variances.
Yep. I'm assuming equal variances here, right? So I'm going to interpret this top row, right? And when I interpret this top row, here's my test statistic. Here's my degrees of freedom for my test. Here's my p-value for my two-tailed test, right? Here's the mean difference. Here's the standard error of the difference, right? What happens if I take my mean difference and divide it by my standard error of my difference? What do I get? What is it, Sam? Yeah, you get the t-test, right? I mean, this is just giving you all the pieces and parts, right? And then I have 95% confidence interval around what, Sam? The mean difference, right? So the mean difference in satisfaction among my men with PTSD and my women with PTSD, point estimate is 28.6 with a lower bound of negative or 2.45, upper bound of 54. Is that a small? What's going on with my confidence interval there? It's massive, right? But I've got 24 degrees of freedom. I don't have a whole lot of people in there, and so this is going to be a pretty big difference here. Okay, so people seeing where we're getting all this. This is all stuff that we've calculated by hand. SPSS is just laying it out for you, nice and easy. Okay. Questions about this or anything that we would grab for in terms of our interpretation? Yeah.
I was gonna ask, like, the T's are like negative. Does the like direction matter?
Does the direction matter?
Because we're just looking at differences, right?
It's completely arbitrary, right? If we put, so who, and this is the other thing too, looking at here, it looks like men are reporting less marital satisfaction than women among our accident survivors with PTSD, right? And based on our tests, even though we have an incredibly small sample, it looks like men with PTSD are reporting systematically less marital satisfaction than women with PTSD. Now, what we make of that is going to depend on our research question or a theory and things along those lines, right? But even with this small sample, it appears that we have evidence of something that looks like a reliable difference in marital satisfaction across these two groups. But this negative t-test is just saying that, I guess I took men's mean and subtracted from women's mean. Well, I would have recoded this so women were 1 and men were 2. What would my t-test have been? It'd be positive, right? This is completely arbitrary, okay? And so this is why when I'm reporting effect sizes, I often won't report negative effect sizes because the sign is arbitrary for means-based tests, not for correlations. Sign for correlations, but for effect sizes for mean-based stuff, it doesn't make any difference as long as you're telling me that yes, it looks like men are scoring lower or reporting reliably less marital satisfaction than women in the population of individuals experiencing post-traumatic stress disorder following motor vehicle accident. Now, what would have happened, Alex, if we would have assumed equal variances not, or had equal variance not been assumed?
Changed in values.
Yeah, Okay. What we're doing here is if we were to have assumed, run these analyses, not assuming equal variances, we use this second row, which is a scatter weight solution that we had talked about previously. You'll see that we've had a significant downward adjustment of our degrees of freedom, right? Our test statistic is different, and so equal variance is not assumed. We're going to go through and we're going to use this line here, right? But same thing, if I'm going through and I'm calculating a confidence interval with equal variance is not assumed, this is the confidence interval I should be using, right, versus this one up here. So whatever you decide to use, making sure that you're remaining consistent with stuff. Now, Howell, if you've read that chapter, Howell makes arguments, and people have made arguments that this is the more conservative. This becomes asymptotically close to equal variance is assumed as you have less and less of a violation. And so there are arguments to be made that you should just always use equal variance is not assumed, right? But convention is to look at your Levine's test if you haven't had a violation there, to just report equal variance is assumed. Okay. Questions on any of this? All right. If we go down through and we take a look at Marlowe Crown social desirability, do we find that men with PTSD following motor vehicle accident are reporting systematically higher or lower levels of social desirability than women with PTSD? And what is our general conclusion here? What do you think, Rajiv?
I think it's higher.
What's that?
So I think they are reporting higher values, I guess.
Based on our statistical test, do we have sufficient evidence to conclude a reliable difference in social desirability in the population of men and women?
Yes.
If we look at our hypothesis test, so this is, and it doesn't matter if you're not familiar with social desirability as a computer science person, I'm fine with that. That's not really the point. But if we go through and we take a look, right, if we assume equal variances, we've got a p-value of 0.913. So we reject or fail to reject the null hypotheses.
Failed to reject.
Fail to reject the null hypotheses, right? We say our confidence intervals around our difference are almost perfectly centered around 0, right? So the only thing that I might take a look at here, right, is so you've got a marginal effect for violation of homogeneity of variance for your Marlowe Crown, which suggests that even for this underpowered test, we're approximating getting close to identifying a violation. So maybe I might take that into consideration on whether or not I'm assuming equal variances or not. But at the end of the day, it doesn't matter, because neither one of these are even close. So for these types of things, you can just talk about, yeah, we fail to reject the null hypothesis, you don't have sufficient evidence to claim a reliable difference between men and women in social desirability based on these data, right? Now, what if your significance test was 0.054? Would I be happy with you saying that you failed to reject the null hypothesis and say that you don't have sufficient evidence to claim a difference? Now, why is that, Steph?
Because we wouldn't provide enough information about those considerations of the violations of assumptions and how they might have affected your
Right.
evaluation.
We might have something like that to talk about, right? We're also p equals 0.05. I don't know if everybody's willing to make a commitment today in this room that anything that is p equal 0.05, you're going to throw out the door and say, nope, there's nothing there, right? Particularly in samples of 26, right? You probably want to say something more technically. We haven't met our standards, and so our technical decision is to reject the null or fail to reject the null. But at that level, that p-value is marginal. Some people don't like that, but it's close, right? And we probably want to say a little bit more about that. So yes, we didn't meet criteria for statistical significance. However, we're working with no people and we'll probably calculate an effect size and have a conversation about that. So even though it doesn't look like we weren't able to claim a reliable effect in these data, it looks like things are going in the right direction. This is the effect size, and talking a little bit more about that. Here, that's nowhere near close, right? But in general, thinking about how we approach things. What's the last thing we might want to do for these in these data? What do you think, Sam? What are we missing in our lives these days? Effect size, absolutely. In this situation, what might we want to do in terms of choosing our what's going to be our best bet in terms of choosing the standardizer? Hedges, Weiss hedges. Okay, we have unequal sample size. That's a big one. And then what else? Why not blasted delta? Yeah, we don't have a reason. I mean, it's been, I don't know, the one does the other and say, oh, like, this is the thing, right? So what we would probably want to do here is calculate our hedges G. Now, we could,
Would we use the unbiased hedges G?
yeah, we probably want to go through and add on that. All right. So what do we do? I'm going to ignore that. What do we need to do first?
Wait, did someone flip a light on?
Yeah. All right. So we're going to calculate hedges G. What do we need to do first? Right. And so our pooled variance, right, is going to be male sample minus 1 times what? Variance, okay? Watch out, because if you put the standard deviation in there, you're going to be sad, because you'll be wrong. So 922.094, where did I get that? I just squared the standard deviation, right? Plus 21 minus 1 times 596.092. Okay, so I've got sample 1 minus 1 times the variance, sample 2 minus 1 minus 1 over the variance over 5 plus 21 minus 2, 0.426. Okay, I'm going to use that for my effect size. Nope. What do I got to do this? Yeah. If I take that, my pooled variance is going to be 25.503. So people follow me, see where I got calculating my pooled variance? You get really good at this because you do it a lot, okay? And so now, calculate my effect size. What do I need on the top of my effect size? Yeah, mean difference. Do I need to calculate mean difference, or does SPSS give that to me? Yeah, so that's going to be 28.644. Just pulling that from my output, divide that by 25.503, which is my pooled variance estimate, make us off. People will often call hedges G, just call that D, but we'll just keep it simple here. A sample effect size of 1.12. Lauren, can you give me an interpretation of that effect size? What's that? It is large, yes. Can you give me more than that?
Yeah, would it suffice?
It would be, is it effect sizes where you use the standard deviations, so it's over one standard deviation.
Okay. Yes, but then fill in the blanks and tell me what that means so that it means something to me.
Well, good question, because I don't really know what it means.
What are the variables? Who are groups? What are the variables?
Oh, yeah, men
Yeah.
and women. Which one were we, oh.
The
Hold on.
lock walls.
Okay,
Yeah.
so men scored lower,
Uh-huh. How much more? Low?
one standard
Yeah.
deviation, above
Below, who?
one.
On.
The block wall is
Yeah,
total.
there we go. Right. It's sort
Baby
of
steps.
fill in the parts, right? Right? And so what we would say, like in terms of like making this mean something, people say, based on these data, our data is suggesting that on average, men are scoring over a full standard deviation below women in terms of marital satisfaction when we're looking at men and women who have diagnosis of PTSD following a motor vehicle accident, right? So tying all this stuff together, and that's a big deal, right? If one group is scoring a full standard deviation, on average a full standard deviation below another group, that's a big effect, right? If we said, hey, this person's scoring a standard deviation above the mean, like, that's a pretty elevated score, right? So, and does it make sense that we found a large effect size in this example? Yeah, you're shaking your head, yeah, Alex, why?
Because it doesn't take sample size into consideration.
Okay, it doesn't take sample size into consideration, but why does this match up? So we rejected the null hypothesis, or we rejected the null with a sample of next to 0, and then we find that the effect size is quite large. How does this all tie in based on our understanding of things? With a sample of 26, would we have found that this effect size was, say, 0.4? Probably not, right? Because basically we've found a statistically reliable effect with a tiny sample because we're looking at a difference that's pretty massive, right? It's a pretty substantial difference. And so even with our very, very limited sample, we were able to determine or reject the null hypothesis and claim statistical significance here. But maybe we didn't. Maybe we failed to reject the null hypothesis because of p-value is 0.07, right? But then we calculate our effect size and we find our effect size is 0.7 something. Is that something that could happen in the world? Absolutely, right? And then that might be a case where we'd say, well, we failed to reject, or we failed to reject the null hypothesis, saying we don't have sufficient evidence to conclude a reliable difference between men and women in terms of marital satisfaction following a motor vehicle accident. However, the effect size found that men were scoring 3/4 of a standard deviation below women in terms of average marital satisfaction. Note that we have a small sample size likely contributing to our failure to detect an effect. They're pulling all this stuff in, and this is where your effect sizes start to become important because they add more context than just up and down vote for your p-values, right? It gives you a better sense. You're able to say, yeah, we failed to reject the null hypothesis, but we really had a limited sample. If we're actually looking at effect sizes, it looks like there's nothing there, right? And gives you a little bit better interpretation of things. Okay. So people seeing how we start to integrate these different components and how we can start to provide more meaningful and reasonable interpretations of our data as opposed to just, is your p-value greater than less than 0.05? Okay, cool. All right. Yeah, Rajiv, what's happening?
So don't we need to calculate the Hedges unbiased in
Yeah,
this case?
we would. I'll let.
Right?
Yep, we would. I'll let you do that
Okay.
on your own. But yeah, basically with Hedges unbiased, then all we gotta do is we take that G that we
Yeah.
calculated and then just tack on that correction factor and you're good to go. And you're absolutely right, in this case, unbiased G is probably what you, because this is a really small sample, right? And what we're gonna get a larger or smaller correction for that effect size with sample 26. Probably pretty big correction, right? I mean, that's gonna drive that down a noticeable amount, because again, our concern is that, given the size of our sample, we probably overestimated that in terms of what's close or reasonable for the population parameter. Effect sizes, just like any other statistic, have a distribution, right? Not every sample that we run the effect size that we get is gonna be equal to the population parameter. We're gonna get some that are too high, some that are too low, some that are kind of close in the middle. This is why we spend so much time talking about distributions and thinking about distributions, not only means, but of test statistics and of effect sizes and all this stuff, in terms of starting to get you thinking that, hey, even just because I found in my study this one effect, I can basically tell nothing from my one effect, because it's likely, probably, I'm somewhere near the middle, right? My best guess is that I'm somewhere near the middle, but I also have to keep in the back of my mind that I could be way out on one of the tails, right? And then use that to make a determination on what the next steps are for your research. All right, so in terms of like write-ups for your independent sample t-test, you all are capable of reading. I won't walk you through unless we want to let Rick do it in the NPR voice. But go through, so this is an example of, for an assignment, like how we might start to pull these things together and start to incorporate different components into something that's reasonable. Again, please don't cut and paste this, but you can go through and start to see kind of where my mind's at and what I would like to see in terms of integrating things together. For a t-test, independent sample T for like a manuscript is going to be shorter, because you don't need to convince your readers that you know everything about all the nuances like you do me. So it would be something considerably shorter. But again, this idea of we're providing test statistics, we're providing means and standard deviations and some of this stuff to try and pull all this stuff together. Okay, so do go through and take a look at that. All right, last thing we're going to talk about is repeated measures. Repeated measures, I like to call repeated measures working efficiently. With a repeated measures design, what we're doing is we're looking at the same group of individuals on one or more variables across 2 or more occasions, right? So I've got all of you, I give you a pre-test on how much you know statistics, and then when I catch you at the end of the semester, I'm going to do it again, right? I've got the same people testing you across multiple occasions. If I wanted to see whether or not we have a change in statistical knowledge, I would probably think about using a repeated measures test here, okay? Now you'll see that I have an asterisk right here. Asterisk right here, anybody have an idea, if they're familiar with repeated measures designs, why I might asterisk this idea of having the same group of people and measuring them on multiple occasions? When else might I use a repeated measures design?
To compare something with the same subject.
What's that now?
To compare between 2 different scenarios with the same subjects.
With the same what?
With the same people or with the same like the same subjects that we're using.
Yeah, kind of like your matched groups, right? If I've got a group of people, I can't measure people on 2 occasions, but I've got this group of people, and then for every person in this group, I've got this a different person, but they're matched on this list of characteristics. If we've got a matched sample test, we would still use we could still use a paired sample t-test, because it's, even though they're different people, we're assuming that they're the same on all the variables that matter to us, and so then we can still use this as a paired sample test. So if you've got a matched group design, this is something where it would be appropriate to use a paired sample as opposed to an independent sample, and we'll talk about why the paired sample has some pretty substantial advantages over the paired sample, or excuse me, over the independent sample. So benefits of our repeated measures designs. Repeated measures designs map on nicely to a lot of the types of things that we would like to look at within psychological science. this is how you are, and then I do something to you, and I see how you are after that. So in terms of treatments, right, in terms of different types of experimental manipulations, education types of things, right? Here we are, we gave you some training or did something, and then looked at you afterwards and seeing if we're seeing some sort of difference on this outcome, okay? Also a more efficient use of our resources. Angeline, why is this a more efficient use of our resources? Yeah, I don't have to recruit the whole number of people. Like, okay, here's my one group of people, and I'm gonna recruit a whole another group of people, and I'm gonna give them some manipulation. So now I've got twice the sample I need to get and run. If I can just take these people, measure them, and then do whatever I was gonna do the second sample, just do it the same person. You can't always do that, right? But if I can, much more efficient use of resources, and then an increased ability to account for random error, right? What we see is that if I take all of you and measure your scores today, and measure your scores tomorrow on something, what we start to do is you serve as your own control. So if we get weirdness in terms of just how you respond to things, right? Morgan tends to score on the low end of all of her scales. Candace tends to score on the high end of all of her scales, right? And if we're just comparing Candace and Morgan, we've got a huge difference because Candace and Morgan approach things differently. But if we've got Candace and Morgan, and that's my only sample, Candace is probably going to respond similarly tomorrow the way she would yesterday, and we get that sort of taken out, and so what we are left with is sort of the change that's specifically attributable to change in Candace. Same thing with Morgan. Thinking about this in terms of like, so we do in our lab some physiological stuff. Anybody done work with physiological variables? No? So things like heart rate, skin conductance, things along those lines. People vary, huge individual differences, right? People across a whole range. And so if I wanted to say, see if I had some video prime, they got people physiologically activated, right? What I could do is I could measure everybody who was just sitting there watching some neutral stimulus and measure their heart rate and skin conductance. And then I could bring in a whole new group of people and show them my emotion prime and measure their heart rate and their skin conductance. And I would hope that the heart rate and skin conductance would increase, indicating physiological activation in the second group. But there's a whole lot of mess, right? There's a whole lot of differences, right? And it's going to be a lot harder to detect that effect. But if I'm taking the same people and I sit you down and I have you watch this and I measure your skin conductance and heart rate when you're just watching some neutral sort of stimulus, and then I go through and I show you the emotion film and you're watching it now, all those individual differences, you serve as your own control, and all we're getting is just a change, okay? And so what ends up happening is when we're running our paired sample test, we're using our paired sample t-test to look at scores within individuals across repeated measures, with the exception of recognizing sometimes we've got match pair designs that we use, okay? And what serves, and this I can't look at you like in the eyes, this is so important for you to know, difference scores. The difference between time 2 and time 1, this is your primary unit of analyses with your paired sample t-test, okay? We're going to get in our raw data, we're going to measure you at time 1, and we're going to measure you at time 2. But what we're really interested, our main unit of analyses is the difference score. The difference score is what we're interested in, okay? And so for our paired sample test, our null hypothesis is that the mean of the difference score in the population is equal to 0, okay? Our alternate hypothesis is the mean of the difference score is not 0, okay? What we've got is we've got some population, and we've got some set of different scores, some distribution of different scores in the population. We're going to draw a sample from which we're calculating those different scores. If things don't change from time 1 to time 2, what's the difference? 0, right? There is no change, right? But the whole hypothesis, our focus of our analyses is on these different scores, okay? Do different scores across multiple assessments deviate sufficiently from 0 to conclude a non-zero difference in the population? Again, we're still working on a population. It's just this population where we've sort of looked at the difference between time 1 and time 2 multiple occasions. Our sample is just looking at that, okay? But our unit, our metric, our output is difference scores when we're working with a paired sample test. Okay. So what is the distribution distribution of sample means that we're looking at with a paired sample test, Morgan?
I knew you were gonna call me. Which means I have slightly no idea.
But I think you do. What's your best guess? So what distribution of sample means are we looking for in a paired sample test? What's the value? What's the value that we're looking at the mean at the mean of?
I feel like I must not know what you're asking because it seems really obvious, but I still have no idea.
So no. Tell me what you think is said.
I don't have an answer. But I don't know. I don't necessarily understand what you're asking.
What's our variable that we're charting means on with a paired sample test?
Differences?
Yeah, right. We're just looking at the difference scores, right? And this is all we're doing. So instead of just like a raw mean, but it starts to get confusing. Like, well, we got these scores at time 1, we got these scores at time 2. Which one's important? Neither one of them. Doesn't matter, right? What we're looking at is the mean of the difference scores and seeing whether or not those are different. Right? And that starts to have impact on thinking about how we're going through screening these data in order to sort of get ourselves set up for stuff. Okay? So, paired sample test. Our T statistic for our paired sample T is going to be the mean of our difference scores minus the mean under the null. What's the mean under the null? 0, so that cancels out. Over the standard error, the mean of the difference, right? Standard error, the mean of the difference is just the standard deviation of the difference scores over the square root of n. Does this look familiar to anybody? What's that?
Is what?
Like this whole setup? Where have we seen this general setup before?
Single sample test.
Perfect. Excellent, absolutely. All your paired sample tests is just a single sample t-test, just with, you're just using, you've got your one sample of difference scores, right? And you're testing it against 0. It's the same formula, it's the same thing. You're just using now calculating difference scores that you've got at time 1 and time 2. And so our standard error of our difference scores is standard error of difference scores across assessments. Our expected mean of the difference. We're looking at the expected mean of difference scores in individuals across repeated measures, assuming that the null hypothesis is true, assuming that there's no difference, right? So here, we've got participants A, B, C, and D. We've got their scores at time 1, time 2, or time 1. We've got their scores at time 2, and then we've got our difference scores, right? This is what we're concerned with. This could be anything. This could be anything. Does it matter if the distribution of scores at time 1 and time 2 are skewed? No, they could be the craziest distribution you want. Doesn't matter. As long as when we subtract time 2 from time 1, that difference score, as long as those difference scores have a reasonable distribution. Here is we're going to calculate our difference scores. We're going to get the mean of the difference, standard deviation of the difference. This is what's going to go back into and calculating basically what ends up being a one sample t-test. Rajiv, I'm sorry, I sprinted at you. It's a scary thing. It's a really slow thing. Like, what is the slow-mo object coming at me? But you're exactly right. Okay. And again, this is just our single sample t-test that we're running. It's just all we're using is our standard deviation, our mean standard deviation of difference scores. So the question is, what's the probability of obtaining a set of difference scores with mean of 3.5, assuming that the null hypothesis is true? People kind of get this. I mean, it's really simple, but it can be difficult to wrap your head around if you get fixated on time 1, time 2. Questions about this? Yeah.
Is this set up like the equation the way it is because we're kind of referencing something?
Can you explain that to me?
Like, you know, in independent samples, like the direction of the difference didn't matter.
Mm-hmm.
But here, like we're kind of...
It's still arbitrary. In general, what I'll encourage you to do is set things up so you're subtracting time 2 from time 1. Lauren, what happens when we subtract time 2 from time 1? Yeah, right. Your sign is consistent with your direction, right? because if I subtract time 2 from time 1, if I've got positive difference scores, that means I have an increase. If I have negative scores, it means I've got a decrease. You can flip them around and do that. It's just you don't have intuitive signs on your test statistic, but it makes no difference. It doesn't change anything. So assumptions of our paired sample test. Outcome variable is continuous, and the sampling distribution or difference scores in the population is normal. Okay. Again, don't care about sample 1, don't care about sample 2. What we do care about is that the sampling distribution of the different scores is equal. Informal assumptions, we don't have outliers, right? We've got everybody showing 4 to 5 point increase, and then someone else has a 20 point decrease. That's going to be problematic. We want to figure out what's going on there. Okay. Our effect sizes. This starts to get a little tricky, okay? Our task with our effect sizes is always, what's our standardizer? How do we want to go through and standardize this? And things start to get a little bit difficult with our paired samples. Mean difference, again, a really intuitive effect size as long as we're looking at something that makes difference. It makes a difference, right? Again, go back to Josh Clapp's weight loss program. I find that people on average dropped 15 pounds on my weight loss program. Does that make sense to people? Yeah, that's a lot of mass, right? Like, this is a big thing. So I can just say, hey, people on my weight loss intervention lost an average of 15 pounds. That's meaningful, right? But if I say people on average drop 12 scores on the PCL, that's less meaningful, right? Which is the problem we run into with our arbitrary scales and measures and things like that in psychology. And so our options are Cohen's D, okay? Cohen's D is just the mean of the difference over the standard deviation. Once again, what's our concern about just this standard Cohen's D, Rajiv?
The standard deviation.
Yeah, which standard deviation, right? Standard deviation time 1, standard deviation time 2. I don't know what standard deviation you're talking about, okay? We have a variation on Cohen's D that what we can do is we can just go through and take the square root of the average variance. Okay? What's the square root of the average variance? What's the analog of that? What's that? Okay, now be careful. It's actually this gets down into this piece of things. When have we taken the square root of what's the analog of this in pooled, right? But why don't we need to worry about a pooled variance estimate in our paired sample test? Okay, yeah, because we have the same people, right? We can't have different sample sizes at time 1 and time 2. We have to have the same people in both things, right? And if we have the same people in both, I mean, you can use your pooled variance estimate or your pooled variance formula, but it's gonna be the same as the average, right? And so what we can do then is, if we want to calculate a Cohen's D, is we can just take the average variance at time 1 and time 2 and take the square root of that. What I will note is that the average of your variance here is not the same thing as the average of your standard deviations, right? If you take variance 1 and variance 2, take the average of your variances and then take the square root of that. That's not the same thing as taking your standard deviation at time 1, standard deviation at time 2, and taking the average of that. Those are not mathematically equivalent. They're close, they're probably close, but they're not the same thing, okay? So standard deviation, or the square root of your average variance is not equal to this your average standard deviation. So make sure that you have to start with your variance. Start with variance, take the average of your variance, then take the square root of that. Don't just average your standard deviations, because you're going to get the wrong value. People see what I'm talking about here? Okay. So this is basically the functional equivalent of our hedge is G. We're just using the square root of our average variance. And then we can also calculate Glass's delta. This is nice, particularly for paired sample tests, if we have a reasonable baseline, okay? Which we often do because we have you here when we weren't doing anything to you, and then we have you here where we're screwing around with your motions, like because then it ends up being a nice way, because our standardizer is the standard deviation or our variability in terms of where you were at rest, not messing around with anything, right? And so again, all the reasons we might go through and use Glass's delta, same reason, same thing as we were doing before, okay? And then also, you'll sometimes see R squared provided as a metric of effect. This is a metric of association. You can calculate this using your test, squaring your test statistic over this, your square of your test statistic plus your degrees of freedom. That'll give you an R squared effect size for your test. But I like the means-based tests and sort of these things because it's intuitive, right? You can. This is a measure of association. It's going to tell you, you know, the proportion of shared variance and means at time 1 and time 2. It ends up being a weird thing. It's easier for me to say people in my weight loss program dropped an average of, you know, 0.8 standard deviations relative to where they were at baseline. That makes more sense to me. Okay, so I encourage you to choose from one of these things. Okay, questions about this? All right, other thing that we can do, and I'm going to encourage you not to do this except for in select situations. We could also go through and calculate our D, use standardizing D using the standard deviation of the different scores. Okay. We will talk about when we need to do this. We need, if you're going to calculate a confidence interval on your effect size, this is the point estimate you need to calculate. But the concern with this is that you're going to end up with an overestimation of your effect size. Okay? Because what happens, and let's say I have a treatment study, okay? And pre, post, right? This is 100, and this is 50, and this is 130, 150, 75. Okay. And let me say this is 81. 30. What's the variability of my scores here? And I'm not looking for an actual number, but do we have a lot of variability or not a lot of variability? What do you think, Alex? You're shaking your head. Decent amount of variability, right? And what about at time 2? Do we have a lot of variability here? Yeah, a lot of variability here. But if we look at our difference scores, okay, what's our difference here? 19, 20. What about here? 32. What is it? 25. What about here? 30. Okay. What's our variability of our difference scores? Not a lot. Okay. And so this is the key thing. This is what makes your repeated measures test so powerful, right? Because if we were to treat this as an independent sample t-test, right? our standard error is gonna be a function of a big variability estimate plus another big variability estimate. Our standard error is gonna be extremely large, right? But if we're looking at the standard deviation of our difference scores, even though we're kind of all over the place, the amount of change that we get is pretty uniform, right? And so again, thinking about that physiological example, people may come in with resting heart rates of all over the place, and people may come in with resting skin conductance at very high, some people more sweaty than other people, right? But if we see everybody change systematically in response to this in a very systematic way, the variability in our difference scores is actually quite low, right? And so this is what happens, and this is what makes these repeated measures designed so powerful, is because this is the variance estimate that we use. One, we're only using one variance estimate instead of two with our independent samples. Two, the standard deviation of the difference scores is often considerably less than the variability of the first assessment, variability of the second assessment. And so why might we be concerned then that if we take standardize our effect size using the standard deviation of difference, well, that's going to be a problem? What's it going to do to our estimate of effect, Sam? It's going to blow it up quite a bit, right? Because what we're doing with if we use the average of our pooled variance, we're going to take pooled variance, or the average of our variance, we're going to take these two variance estimates, we're going to take the average and use that as our standardizer, right? Because we're measuring our metric in terms of standard deviation at time 1 and time 2. Or if we use Glass's delta and we just use this time, we're standardizing our effect size in terms of the metric of variability at time 1. But if I go through and I standardize my metric in terms of standard deviation of the difference scores, one, it gets difficult because I'm telling you that I get a standard deviation unit change in my outcome based on standard deviations of change. It's a weird thing, right? Whereas here you can say we see a standard deviation unit change in terms of variability that we see at time 1. Makes a lot more sense. So one, interpretively, it's weird. Two, we're also concerned that it's going to blow our effect sizes up through the roof. And we're already worried about our effect sizes being blown up through the roof just based on publication bias, right? We're only publishing the stuff that ends up probably having larger than expected effect sizes because those are easier to detect effects. And so the concern here is running into situations where if we use the standard deviation of the difference scores to standardize our effect, we're going to get stuff that's systematically too large. You'll also see for effect sizes for test statistics used based on this D divided by 2 times 1 minus the absolute correlation of the measures at time 1 and time 2. This is an important thing for power. Do not use this as your metric of effect. This will shoot things up through the roof. It'll make your effect size be way, way larger than if you're calculating one of these. Okay. Now, when we get into calculating effect sizes around, or confidence intervals around your effect size, if you're going to calculate a confidence interval around your effect size for a paired test, then we're stuck with this. Then we have to use this because our standardizer for our point estimate has to be the same as the standardizer we used in the calculation of our test statistic based on reasons we'll get into. But in general, if you're just calculating a regular effect, these are the things that you're probably going to be thinking about using. Questions on this? All right. Okay. So strengths of our paired sample t-tests. Okay. Again, these are things that are mapped nicely onto stuff that we typically want to look at, like education stuff. I'm doing this, and here's an intervention on reading. Does it make people better, right? If I, shock somebody, what happens to their level of fear, right? These types of things. It's stuff that maps on well. we've got a more efficient use of our resources, and we've got a huge reduction of error that's attributable to individual differences, right? When we go through and we create those difference scores over here, all the individual differences get sucked out, and all we're looking at is just change across people, right? So all the individual differences we see in where people start in treatment and where people end, that gets sucked out, and we're just getting a pure measure of how much they've shifted across time. And so people are acting as their own controls, and so what ends up happening is the variability of our difference scores is often generally less than the variability at time 1 and time 2. And then when we're calculating our standard error, we're just using one variance estimate instead of 2 like we would for an independent sample test. And so we've got far, far more powerful tests. You will detect, you will identify differences as statistically significant at a much higher rate with a paired test than you will with an individual test. They're just infinitely more powerful tests, yeah.
So if it's a more powerful test, does that mean that we can use fewer people?
Exactly, right. You can detect
What's the general guideline for how many people we would want for a person?
Well, that's going to be, you're going to need a power analysis for that, right? So are you expecting people to change a lot, a little? But in general, the number of people that you're going to need to detect a reliable effect if you're working with a paired sample test as opposed to an independent sample test is exponentially low. Like, it's shockingly lower, right? So in any cases where you can use a paired sample test, use a paired sample test. However, there are some times when we can't use this, okay? Influence of time-related factors, right? If something is going to happen, right, over the course of time that's going to confound our stuff, then I can't use that, right? If I'm looking at, if I'm looking at something that is going to accrue a whole lot of confounding variables over time, then I may not be able to use a paired sample test. The bigger thing that ends up happening, practice effects, right? This is why we can't, in psychotherapy, go through and say, all right, here's your CBT intervention, and then we're going to take the same people and going to give you a psychodynamic intervention and see which one of those are better. Because I can't tell you to forget the stuff that you already had this. Like, this is now knowledge that you have. I can't now ask you to forget it and move on to something else. Or I want to see whether or not you perform better on this exam using this study method versus that study method. Because if you've already taken the exam, you already know the answers, and I can't ask you to do it again because that's going to be, there's going to be practice effects there or order effects, right? Maybe if you're in one of my conditions, it completely ruins you for all the other conditions, and so I can't incorporate that in without accruing so many confounds to my inference, right? So there are reasons where a lot of reasons times where you can't use a paired sample test. But if you can, if it's possible, if you can put together a repeated measures design, strongly encourage you to do so, just because it's going to increase the power of your tests by a great deal. All right, let's go through and finish up with our paired sample test on our screening. Pull up this interpersonal paired test here, this data set. And if we take a look at our paired sample screening, what we've got is a number of these. So these distant, distance is interpersonal stuff. What we've got is data collected from people who have undergone treatment, and we're looking at whether or not we see shifts in personality types, ways of, or interpersonal characteristics among these individuals. Distant is cold, distant interpersonal style, so this is going to be sort of being very disengaged with people, versus SAC is self-sacrificing. This is people sort of doing too much, putting themselves out there, doing way too much, right? And so we've measured people, this small group of individuals, on these two variables at baseline and at post-test. And what we want to see is whether or not we have evidence of change in these different interpersonal characteristics before and after treatment. Okay? And so, what we're going to do, so what is our unit of analyses for this example? For our paired sample test, what are we actually interested in? What do we need to screen?
The difference?
The difference, exactly, right? So we could go through and take a look at time 1 and time 2 if we wanted to, and you might want to just to kind of see, but at the end of the day, that's sort of irrelevant because our distribution can be crazy wonky. All that matters is our difference test, right? So what we're going to do is we're going to go up to transform. We're going to hit compute. And I'm going to calculate distance diff is going to be equal to distant at post minus distant at base. Okay. Again, I'm putting my time 2 first in this subtraction because what's going to happen is then if I have positive values, it'll say that my cold and distant behaviors have increased, or negative values, my cold and distant characteristics have decreased. Okay. And then I'm going to go ahead and hit paste. All right. So we've got that there. And then, because working through that is a pain, I'm going to compute SAC difference is SAC post SAC base, and there we go. Okay. And Lauren, what is this going to do for me?
We're going to see the differences.
Yep. Is it just going to go through, if I go through and run this now, we'll see in SPSS, I now have 2 new variables. These 2 new variables is is my actual difference scores here. These are the things that SPSS, this is what SPSS is going to be doing in the background, right, running. I just need to calculate these different scores so I can screen and take a look at stuff. Okay? People understand why we went through and calculated different scores? So what we're going to do now, so we've done before, we're going to go analyze descriptives, take a look at our descriptive values, options, skew, kurtosis. Okay. Now the one thing you may want to go through and look at your actual raw data scores. What's the one thing we might want to take a look at the values at time 1 and time 2 for in our screening?
And then the max.
Yeah, to make sure we don't have any funky values that are falling outside of what we would expect, right? But in terms of our actual screening, what we're going to be most interested in, and we'll save our Z scores here, is our descriptives. And so if we go through and we run this, what do you say, Rajiv? Anything going on here that might cause us to worry? No, I mean, our sample's small, right? We've only got 19 people in our sample. But what's exciting is that we've got a crazy powerful test with our repeated measure test, right, where everybody's serving their own controls. Variability associated with individual differences is getting sucked out of this business. All we're looking at is just straight up change. It doesn't matter where you start or where you end. It's just how much of that you've changed. So min and max doesn't tell us a whole lot because we could have out of bounds values and that wouldn't show up there, which is why we might want to go through I probably would want to go through and just screen our minimum and maximum values somehow and make sure that all our scores were within bounds, that we don't have implausible values. We've got our mean, our skew and kurtosis values all look pretty reasonable, so nothing too much going on there that would cause us concern outside of noting that we have kind of a small sample. If we go down through now and go to analyze descriptive statistics, explore, and let's ask for our, again, we're interested in screening our, basically what we're doing is we're getting graphs for our outcomes. Do we have any does anything need to go in the factor list here? Nope, we're good to go, but I will put my research ID down on my case label. That way in my box and whisker plots, if we have extreme values, it'll label them by their participant number so that I know which ones they are, right? I'm gonna go to plots, ask for a histogram, turn off stem and leaf. You can put print stem and leaves if you want, I just don't clutter things up. So I'm gonna hit continue there, I'm gonna hit paste. And obviously you can just hit sort of whatever you want, but all right, so again, we've got our processing summer up here. All of our descriptive statistics for our difference in our cold distant variable, our difference in our self-sacrificing variable. Here's our difference in our cold distant from pre to post. What do we, anything remarkable about this? And I would say sort of histogram, different score approximating normal distribution. Things are looking pretty good, right? Box and whisker plot. Things are looking all right. No values more than 1.5 times interquartile range falling out there. Looking approximating normality. So that's looking nice. Same thing here for our difference in our self-sacrificing. And we got a small gap in that distribution, but we actually don't have a whole lot of people in there. So we've got two values, that 3 and 4 value increase that's kind of maybe a little bit away, but it's not anything that we would call probably an outlying value. Right? Now, if we go down through and take a look at our box and whisker plot, here, again, looks like a fairly symmetrical distribution. We've got case number 2478. What's going on with 2478, Angeline? Yeah, what makes that thing show up as a dot up there? Not a z-score. Okay, because remember these are box and whiskers median-based statistics. So what's that midline represent? The median, right? And what about the bounds of the box? What's the top and the bottom? Yeah, the first and the third quartile. And then the whiskers go out to the most extreme value, falling within 1.5 times your quartile range. And so we've got the score for 2478. And again, you want to remember what we're talking about, right? We're looking at difference from pre to post, or difference in pre to post. We've got 2478 who's demonstrating a change, an increase in self-sacrificing behavior that's falling beyond 1.5 times your quartile range, right? So again, verbalizing this stuff starts to help you sort of understand what's going on. So if we have an increase in self-sacrificing after treatment, is this something that we are excited about or not excited about? Probably not terribly excited. I mean, sort of this self-sacrificing behavior, it's not good. You need to take care of yourself sometimes and not be going out of your way and things. And so we've got an increase, which, I don't know, may or may not be excited about, right? it looks like in general, after treatment, we're seeing a reduction in self-sacrificing behavior, but sometimes things are gonna get the opposite direction, right? And so wanting to identify what that point is, what it means when you're talking about these, so that it's forcing you to think about things a little closely, right? So we'd probably note that case number 22478 has a value on our box and whisker plot falling beyond 1.5 times the interquartile range, indicating relative increase in self-sacrificing behavior after treatment. Are we concerned about this? What do you think, Sam? Are we worried about this score?
No.
No, why not?
I mean, it's not terrible.
It's not terrible.
Yeah.
Looking at our box plot, is that an outlier?
Not
Not really, right? And so this is the thing, don't just identify a point on the thing and say, oh, that's an outlier because of this, right? We want to go through and thinking about what's going on. Now, we typically won't expect an increase in problematic interpersonal behaviors after treatment, right? We hope that they're going down, but sometimes things are going to happen, right? And so this we can identify as maybe a little bit unexpected, but not something that's going to cause us to like run a damn log transform or something crazy like that, right? People understand kind of where we're at with this? All right. And so then the last thing we're going to want to do, go through and take a look at my Z distribution. I'm going to just take that, plot that down, throw a Z in front of that, throw a Z in front of that. Don't need to save my Z scores on my Z scores. I'll get rid of skew and kurtosis here, and then run this. Stephanie, what am I seeing in terms of my values here?
For the, what was DIST?
Cold and distant.
Oh, for the distance variable, it seems fine. They're less than 2,
Yeah.
whatever, 5 cents. For the Z-score, we actually see that value that, you know, what number, 2478, that we see that as a 2.48. That's their Z-score. So depending on what value we chose as an outlier, this may or may not be one.
Right. And so what I would do here is I would identify, this is probably something to note, right? Say in this distribution for change in self-sacrificing behavior, we have a score that's falling about 2.5 standard deviations above the mean. However, evaluation of our histograms in our box and whisker plot, or excuse me, evaluation of our in our box and whisker plot, this is also a value that's falling beyond 1.5 times the interquartile range, and is showing up. But if we're looking at our skew and kurtosis is looking good, so overall distribution is looking okay. If we look at our histograms, this is not a value that's falling. This is continuing to fall along the continuous distribution of scores. This is by no stretch of the imagination anything that we would identify as an outlying value. You know, particularly given a small sample like this, that I don't know if you get a better distribution than that right there, right? So again, wanting you as you all working through these screeners, and again, I'll put something online and some materials up there to help kind of guide this as a framework. But in general, do we have any concerns about our assumptions here? No, looking pretty good, right? Our distributions look all right, but and again, still, it's a distribution of sample means, so even if it does look a little wonky, that's all right, but these are actually looking pretty good. Skew and kurtosis values are looking all right. Values all seem to be within plausible range. I'm not missing any values. I've got 2478 that looks like they've got an unexpected increase in self-sacrificing behavior after treatment, but at the end of the day, this is still probably part of the population of interest, right? I just can't kick out anybody who didn't respond to treatment and then, and then make an assessment of my response to treatment. We're gonna have some people who go the other way, right? And so everything's looking good here. So questions about this? Okay. We nearly made it through this. For the purpose of like tying this all together, so we've got our single sample test. Remember, our single sample test is a test that we're using when we have one sample and we're just comparing it to some known population mean or some reference value, but we don't know what the variance is, right? We don't have a population variance. So this is, remember, our initial transition from the one sample Z into a one sample T test, where we're using our sample statistics for to estimate our independent sample T. We were looking at the difference between samples drawn from two separate populations. We want to see if they're different on some continuous outcome, and then our paired sample looking at continuous at a continuous outcome collected on two different occasions from the same group of individuals, with the exception of matched pair situations. And again, for our paired sample test, our unit of interest is that difference score, right? That it's just, as Rajiv so cogently pointed out, it's just a one sample test. We're just testing this difference score against a reference value of 0. In SPSS, if you calculate those difference scores and you were to run a t-test comparing the mean of those difference scores to 0, you're going to get the exact same values on test statistics as you were if you were to run that as a paired sample test. It's the exact same thing. All right? Cool. All right, folks, thank you so much.